Hi everybody, so in this video I'm going to show you how to use the Taylor series to find the limits of a function. So using the Taylor series to find the limits of a function allows us to approximate a function by a polynomial. Some functions may be difficult to evaluate directly for certain limits. For instance, if we have a limit as x tends to 0 of e to the x minus 1 over x, we can't evaluate this directly because if x is 0, then e to the x minus 1 over 0 is undefined. So the Taylor series allows us to represent these functions as polynomials, making the calculations more straightforward. So in this example, we've converted e to the x as a power series. We can take away the 1, so 1 minus the 1. And when we divide it all by x, this x will divide by this one to make 1, and each of these terms will become 0 when x is 0. So we can see that as x tends to 0, the limit of this function becomes 1. Okay, so if we have a look at example 1, we've been asked to find the limit as x tends to 0 of x over e to the 2x minus 1. So to write this as a power series, I'm going to use Maclaurin series because x is tending to 0. So here we have a Maclaurin expansion. So the first thing we need to do to approximate e to the 2x is we need to find the derivatives of the function. So if we say that f of x is equal to e to the 2x, then f dash of x using the chain rule becomes 2e to the 2x. We can differentiate this again for our second derivative. Again, we can bring this 2 down using the chain rule, so we get 4e to the 2x. And our third derivative, we'll bring this 2 down to make a 4, becomes 8e to the 2x. So we can see that our approximation is centered on 0. So we'll substitute 0 into each of our functions. So f of 0, well, this becomes e to the 0, which is 1. So if we substitute 0 into our first derivative, we get 1 times 2. Into our second derivative, this becomes 1 times 4. And into our third derivative, this becomes 1 times 8. Okay, so we've got our derivatives centered on 0, so now we can substitute each of these into our expansion. So e to the 2x will be approximately f of 0, which is 1, plus f dash of 0, which is 2x, plus f double dash of 0, x squared, so 4x squared, over 2 makes this 2x squared. And then we've got the 8x cubed over 3 factorial, and 8 over 6 is 4/3. So this will give us 4 over 3 x cubed plus all the other terms. So now we've got our expansion, we can substitute this into here. So the limit as x tends to 0 is x over 1 plus 2x plus 2x squared plus 4 over 3x cubed, and all the other future terms minus the 1. And we'll close that bracket. So now we can see this 1 will cancel with this negative 1. And then we can divide all the other terms by the x. So this becomes 1 over 2 plus 2x plus 4 over 3 x squared, and so on. But now as x tends to 0, well, 2x will become 0, 4 over 3x squared will become 0, and all the future terms will cancel to make 0. So what we're left with is the 1 over the 2. What we can say then is the limit as x tends to 0 of x of e to the 2x minus 1 is equal to 1/2. Okay? And in example 2, we're going to look at the limit of a function involving the natural log. Okay, so in example 2, we've been asked to find the limit as x tends to 1 of the natural log of x over the square root of x minus 1. And because x is now tending to 1, we're going to use the Taylor expansion rather than the Maclaurin expansion. So here we have the Taylor expansion, where it is centered on a, and in this case, the a will equal 1. So I'll just write down here, a equals 1. So the first thing we need to do is we need to find our derivatives. And the function we're going to look at is the natural log of x. We might need to look at the square root of x, but we'll come back to this later. So if f of x equals the natural log of x, then the first derivative, f dash of x, will be 1 over x, or x to a negative 1. I'll write both forms. And then the second derivative, so we get negative x to the power of negative 2. And writing this as a fraction, we've got negative 1 over x squared. Our third derivative then, well again, bringing this power down, this gives us positive 2x to the power of negative 3. And as a fraction, 2 over x cubed. So because this expansion is going to be centered on a equal 1, so f of 1 will be the natural log of 1, which is 0. F dash of 1 will be 1 over 1, which is 1. F double dash of 1 will be negative 1 over 1, so negative 1. And f triple dash of 1, 2 over 1, gives us 2. So now we can begin to write the expansion of the natural log of x. We know f of 1 is 0, and f dash of 1 is 1. So this will give us x minus 1 plus f double dash of a is negative 1, lots of x minus 1 squared over 2. So this will be negative 1 half of x minus 1 all squared. And then for our next term, we'll have 2 lots of x minus 1 cubed over 3 factorial, which is 6. I'm just going to simplify this fraction. So the natural log of x we can write as x minus 1 half of x minus 1 squared plus 1/3 of x minus 1 cubed, so on and so on. So now we have our expansion, we can substitute this into here. So we'll say the limit as x tends to 1 of the natural log of x, x minus 1, and we can factorize this x minus 1 out of each term. So we'll multiply this by 1 minus a half. Factor it out of this quadratic leaves us with x minus 1 to the power of 1 plus 1/3 of x minus 1 squared all over the square root of x minus 1. Now we can find a common factor with this denominator by factoring out this x minus 1. So x minus 1 can be written as the root of x minus 1 multiplied by the root of x plus 1. And when I substitute this back into here, the root of x minus 1 will cancel with this one. So what we're left with is the limit as x tends to 1 of the square root of x plus 1 multiplied by 1 minus a half lots of x minus 1 plus 1/3 x minus 1 squared, and so on. And then can you see that as we let x tend to 1, this becomes 1, and each of these brackets becomes 0. So what we're left with is the limit as x tends to 1 of 1 plus 1, which converges on 2. Okay? So I hope you found that useful. Thank you very much for watching. If you did find that helpful, please like and subscribe, and you can download the full lesson and worksheet from my website, mrmathematics.com. There's a link in the description below. Thanks again and take care.